So, shall we start?
Yeah. Time that I show you?
I have my own.
Okay. Okay.
Okay, our next guest is Martin Dickey. He doesn't give a talk about Helenos today, I guess.
Not this year.
Not this year, maybe next year.
I already did at the RISC-V dev room, actually.
Yeah, and it's probably going to be more about microkernels and hardware, right?
Yes. Thanks for the introduction. Thank you all for coming. And when I'm mentioning it, I mean, most of the talk will be about the same topic I have already spoken about at the RISC-V dev room. So if you have seen that, there is no reason for you to see it again, unless you would like to discuss. And again, this is as usual. This is something I always do, more or less like an opinion piece to spark some discussions. So please go ahead and disagree with me. So for those who don't know me, I've been working in operating system domain for some time. I have been working on the HelenosOS project since 2004. I have been working at the Charles University in Prague on the formal verification of HelenosOS. And quite recently, I mean, not longer than 2 years ago, I have joined Huawei, where I'm doing the same stuff, microkernels and formal verification and stuff like that. So I would like to tell you that microkernel multi-server systems are better than monolithic systems. That's it. Thank you. No, really, seriously. I mean, this has been, I would say, an informed opinion of many people for many, many years. And gradually, we got some, I would say, qualitative evidence that this statement is true. But, I mean, qualitative evidence is still just basically a form of an opinion. Now we are gradually also getting quantitative evidence that the monolithic operating system design is flawed. So you have probably noticed there's this paper co-authored by our friend Gernot Heiser, who we had the privilege to see today. And this paper basically looked on several critical vulnerabilities in the Linux kernel and tried to estimate if these vulnerabilities would have been mitigated if we would consider a state-of-the-art microkernel design such as SCL4. And yeah, I mean, you can read the summary here, you can read the entire paper, and it's pretty much convincing. So I mean, this is a single piece of evidence that we are getting in the right direction. We are going in the right direction with microkernels. But, and this brings me back to my original talk at FOSDEM Microkernel Dev Room in 2012, we are paying some price. The price is with the performance overhead. And if you were there, if you remember my talk, I said that it's a fair price, according to my opinion. So I mean, there is no free lunch, but you know, the safety, security, availability, other guarantees that the microkernel provides are you know, counterweighted by some performance overhead that we need to pay. But is it really necessary? Is it really unavoidable? Let's look on this. The microkernel ideas are not particularly new. I mean, the earliest incarnations were already set in 1969. But you know, there was. And there is still some disconnect between the software design and the hardware design. Designing hardware used to be complicated, expensive. It usually required a huge company to back it. And you know, therefore, the operating systems have been written for the CPUs only after the CPUs were out. So not before. I mean, even having a powerful emulation tools like QEMU, stuff like that was not always available. So, you something happened that the hardware designs got stuck in certain ways. I mean, really, try to think about something revolutionary in hardware design that hasn't been there already in IBM S370. I mean, memory management, it was there. Virtualization, it was there. IOMMU, it was there. Offloading, computations to dedicated hardware devices. I'm talking about, so-called data channels. So what was the exact name? I don't remember. It was there already. So there's nothing new under the sun. And the problem is that microkernels suffer because, the current hardware is being designed for the monolithic kernels in mind, or with the monolithic kernels in mind. And therefore, we need to pay the performance penalties due to the fine-grained design, due to the need of crossing the address space barriers, due to the IPC mechanisms and stuff like that. So let's try to change it. Let's try to design the hardware in a better way, or in a way that is more suitable for the requirements of the microkernel systems. I really think that there is this vicious cycle that the CPUs currently don't support the microkernels properly. Therefore, microkernels suffer performance penalties when running on them compared to the monolithic systems. Therefore, microkernels are still not considered, the true mainstream. I mean, yes, we have them on safety critical and mission critical devices. We have them maybe in some embedded devices, but you can have macOS, which is running on Mac, but just as a single server microkernel. But still, we are talking about Linux, and we are talking about making Linux more secure and stuff like that, which is crazy. I mean, the only way how to make Linux more secure is throwing it out. And since the microkernels are still not in the mainstream, there is no strong push on the hardware manufacturers to actually provide CPUs with proper microkernel support, and this closes the vicious cycle. Well, there has been a lot of effort spent on this box already. I mean, for the past 25 years, people have been trying to squeeze out every single CPU cycle from their microkernel code to make the IPC run as smoothly and as quickly as possible. But it was given the limitations of the hardware they had. So and I mean, we have been trying on this too, right? I mean, this is the reason why we are meeting here. So now let's focus on this part. So let's focus on the requirements, on the hardware, and let's focus on creating better hardware to support our microkernels, to finally get rid of this trade-off between safety and performance, security and performance. I got some ideas. I have to say these are very rough ideas, and again, this is something where I would like to spark the discussion. I would like to spark, or inspire people thinking about the actual mechanisms that could be done to make this happen. And my ideas are targeting, the obvious culprits like the IPC and context switching and stuff like that. So first about the problem with the IPC in the microkernel multi-server systems. The finer the architecture it is, the better for safety and security, availability, dependability. But the more we are paying due to the address space, due to the need to move data between address spaces. So, I mean, I probably don't need to explain the problem in very much detail, but compared to the monolithic kernels, where communication between subsystems is just a function call, in a microkernel multi-server system, the same communication is implemented via IPC, which means that we cannot use all the registers for actually passing the arguments, because some registers are reserved for something else. We need to switch to the kernel level, to the kernel privilege mode, and switch the address space and then switch back. We potentially need to do some scheduling in between in case the IPC is asynchronous. Of course, this is not necessary. And if we are moving larger amounts of data, we either need to copy them between the other spaces or establish some kind of memory sharing, which again might be a little bit costly. So what to do about this? One thing that is would be probably quite simple, just implementing richer call or jump instructions that would actually switch the address space by themselves, so that we would save at least the single kernel round trip, where the only thing that the kernel is actually doing here is changing the address space. This could be done by the hardware or by the CPU, and it could be as simple as just switching the current address space identifier. Of course, this still needs to be just a mechanism, just a generic basic mechanism. I'm not proposing, moving some kind of policy from the operating system to the CPU. That would be crazy. So how to do it? Implement by having something like a call gate that would be cached in some kind of hardware cache, like something like a TLB. So the first time this call happens, obviously it will trap into the kernel. The kernel will check, the permissions, capabilities, and stuff like that, and set up an entry into this hardware cache. And consequent calls will be then done just by the CPU. I believe this could be really very simple. Regarding the asynchronous IPC, where there is probably some need for buffering of the messages, I also think this could be optimized. I mean, even nowadays, like somebody already mentioned at my talk yesterday, this could be, this message buffering and message passing could be optimized by making sure that you don't trash the messages from your cache lines. That's fine, but again, I would imagine that the CPU could do it even more intelligently. So basically, using the cache lines as fixed size buffers for the messages, and it's not a problem that it's a fixed size, because in most of the microkernels I have seen that are using asynchronous IPC, the kernel buffers are also fixed size for obvious reasons, that the user space cannot exhaust the kernel memory. So again, I would see that there is a clear separation between the mechanism that could be very, very efficient, very fast, very lean, and the policy that will obviously still stay in software. If you remember Spark v9, this reminds me of the register stack engine that they have there, or stack engine. What was the term? Stack engine or register stack engine? AI64, is it? Itanium. Okay. Well, Spark has something similar. So how about the bulk data? If we really need to move a lot of data between the processes or tasks, currently the current best optimization we have is memory sharing, which actually works quite nice, quite fine. The only problem is that the memory sharing needs to be established and possibly turned down. And if this is happening too often, this causes the performance penalty. And also the data needs to be page aligned. So it's not really very useful for sharing, scattered data structures. It's fine when you need to share, blocks of data that needs to be written to a block device driver or read from a block device driver, but it's not very useful for really, graph structures and trees and stuff like that. So again, an idea that could be something that could be done is to have a new simple layer of memory, of hardware-based memory management that would map virtual addresses to cache lines. Because a cache line is usually something like 64 or 128 bytes, which is much more reasonable granularity for the scattered data structures. And of course, again, we need to, sit down. We need to create a model. We need to evaluate it. We need to implement it in an emulator to be sure how well this will perform. What should be the parameters? What should be the size of this translation buffer? Stuff like that. But I really believe there is some possibility to make this work. Context switching. I mean, we have somehow avoided parts of this context switching in case of the IPC, but still, the problem is that in a microkernel multi-server system, there are more active processes or more active tasks than in a monolithic system. So there will be still some context switching, and all that our hardware is currently doing is basically masking latency. And we have very efficient mechanisms for masking nanosecond latency. That's called the caches. We have quite efficient mechanism for masking millisecond scale latencies. That's I/O buffers. But the context switch is precisely in the middle. It's on the order of microseconds, and we have really nothing to mask this latency. So I mean, I wouldn't say we don't have anything. There is a hardware mechanism quite often used, which is multithreading, and this is precisely why we have multithreading, to be able to somehow make sure that the LUs or parts of the CPU have always something to do, despite there is some data or dependency or waiting for some data. But this does not scale to many threads. I mean, you usually have just a couple of hardware threads, and we can do context switching in software. So how about combining this and having again something like a hardware support for unlimited number of execution contexts. Some of them, the most frequently used, should be cached in some hardware cache, and having some dedicated instruction set extensions to efficiently operate with these hardware contexts. Again, this will keep the scheduling policies and stuff like that mostly to the operating system, but the physical mechanism of quickly switching to a different workload when our current workload is being blocked on the hardware level because it is waiting on some data, that could be done autonomously. We could even think about somehow connecting some other external event triggers to this, like interrupts or exceptions, and this would allow us to do even more stuff. I believe I have a slide about this here. Yeah, that would allow us to do very simply or very elegantly purely user space based interrupt processing. Currently, the interrupts always trap into the kernel space, and in a microkernel environment, what the kernel does, it generates some kind of IPC message that is then being forwarded to the user space driver. If we would be able to do the fast context switching using the hardware, it is just a single step further to extend it to the interrupt delivery to the user space drivers, which would not only make some things faster, it not only would this allow us to get rid of polling in case we are dealing with some very latency sensitive device, where actually even in a monolithic system, the polling can the interrupt processing can be so expensive that polling, despite stupid, is more efficient. But it would also solve the final, I would say, the final compromise regarding the elegancy of the microkernel design, and that's the fact that we still need some device drivers in the microkernel, like the timer. With a direct delivery of the timer interrupts to user space timer driver, we would not need any timer driver in the microkernel. And possibly even moving the scheduler out of the microkernel, which again, is something like a holy grail of many people. Yeah, something would need to be done with the level trick interrupts, the usual pain point. Again, I would say that there is some possibility to have some integration with the platform interrupt controller that would autonomously mask the source of the level trick interrupt when it happens, so that there is no issue with this endless, reassertion of these capabilities. I mean, this is really just this is a stretch. I mean, I did not really find very much useful ideas in my head about what could be done with capabilities on the hardware level, but at least something. I mean, if we just consider the narrow use case of capabilities as object identifiers, again, the microkernel would always need to be in charge of, making sure that the methods called on the capabilities are permissible for that holder of the capability. I wasn't able to think about any elegant hardware mechanism how this could be avoided, but at least for the actual access to the object, the capability ID or the capability reference could be somehow embedded within the pointer itself, and then the hardware would be able to autonomously check whether the access to that given object is allowed by the current context. If you think about RISC-V 128, the 128-bit variant, I believe you could wonder what would be the actual use of 128-bit long pointers. I'm not sure that a flat 128-bit pointer is really so useful. Maybe it is. Maybe I'm wrong, but we could easily divide it into 64 bits for the object offset and 64 bits for the capability reference, and this could work quite elegantly. By the way, I mean, this would be probably even more useful for some managed languages like, I don't know, Java.NET, stuff like that, because they are always dealing with, or the VMs running this managed code is always dealing with the fact that they need to do a lot of bound checking on the objects. And if this could be offloaded to the hardware, it would probably help them a lot. Okay. Some ideas. Do you have something to add to this? Yeah, please.
I'm wondering the Cherry microarchitecture, the Cherry architecture from Cambridge. I mean, they're trying something pretty similar, I think, to what you propose.
And
yes,
I believe
for capability-based hardware.
I believe I have it here. Yeah. So I mean, you might come to me and say, oh, these are just wet dreams. I mean, this is not going to happen. So what I'm now going to present, unless there are other comments or objections, there are some cases or some prior art which somehow leads into the same direction, where I would like to convince you that it is possible to do something like that. It's even possible to do something like that with the hardware we currently have. So imagine the possibilities if we can actually change the hardware. Let's think out of the box. So the first reference is, just a basic paper, rather old, about actually offloading some of the microkernel functionality to hardware. This was done by basically modifying and softcore FPGA CPU, and they were moving, actually complete operations like thread creation and context switching. So I mean, the context switching is something more or less in the line what I have suggested, but the thread creation is probably too heavyweight, I would say. But nevertheless, they were able to measure reasonable performance improvement, something like 15 to 27%. And just speaking about the ways how the hardware could optimize IPC, this has been also done in practice in the wild on the massive parallel architectures. So again, having a lean hardware mechanism for efficient message passing that is somehow connected to a reasonable software abstraction for it. So this could probably work. About the address space switching, there is an interesting paper from the barrelfish people about space jump, which is basically a programming model where a single process uses multiple address spaces at once, and this in that case that was not targeting some performance improvement. It was targeting, just or it was just entertaining what would be the possibilities and benefits of such a programming model for let's say data-centric applications. So I mean, this is not so much relevant to what I have been talking about, but I mean, there are approaches, and they were able to implement this on barrelfish, obviously, and in Dragonfly BSD. So it did not require a huge modification to the kernel abstractions. And if you are old enough, like me, you might remember that if you are running an x86 CPU in 32-bit mode, or probably even in the 16-bit mode, you can still have the task state segment, which is basically hardware-based context switching. It does not have a dedicated hardware cache for that. It just uses regular memory for caching the context. But still, I mean, performance-wise, it's still competitive to the software-based approach. Even the Linux kernel used this mechanism previously, and they stopped using it not because of the performance, but because they just wanted to have a more portable approach. Yes. Yeah, but that was probably just a very artificial limit, because some index in some the global description table could not be. It was basically based on the selectors, and yes. So it was something like 16K or something like that. Yeah, but I mean that's a technicality. I'm not mentioning it that this is the way we should do it. I'm just mentioning it because it has been done. So let's have a look on it and let's improve it. Thank you. Okay, about the cross address space calls. There has been actually a quite nice paper by some of my colleagues from Huawei who have used the VM-func instruction, or the VM functions extension to the Intel VTX, which is something like that. It's a mechanism that allows you to basically do cross VM calls by setting up some call gates, and then just using a single instruction to pass the registers from one VM to the other. So it does the wall switch and address space switch. I mean, switching the extended page tables on the hardware level. And actually, this paper contains an evaluation where they took a rather complex application, something like a web server that uses the OpenSSL library, and they have separated some of the encryption functions, so individual function calls, from the rest of the binary into a dedicated VM, and they have used this VM-func instructions to change it from a normal function call to this cross VM call, and their performance evaluation was quite interesting, because the VM-func function was as costly as just a single system call. So it was not. I mean, it was more costly than just a jump or just a call, but not huge, not more costly. Definitely cheaper than going to the hypervisor, or going to the kernel, going to the hypervisor, making the address space and VM switch in software. So again, I mean, if we would think about this mechanism in more detail, if we would try to improve it, maybe this could really be helpful for the microkernels. Actually, my colleagues are working on some suggestion in that area, and they will publish a paper, or They have already a paper accepted at Eurosys this year. So if you are interested into this, have a look. Yeah, this is what you have mentioned. This is the Cherry capability models. So an evaluation of how the capabilities could be implemented on the hardware level. Again, this allowed them to this was evaluated on a FPGA soft core, but the performance evaluation was very positive, and it allowed them to have basically byte granularity memory protection. You know, again, the limitation is that they have used 64-bit MIPS, so they had to somehow squeeze in the bounds and starting addresses somewhere. So their obvious decision was to have dedicated capability registers, like an extension to the MIPS ISA, which they self-confirmed that this is not so flexible. So how about using the 128-bit pointers and embed the capability identifiers directly in them? Actually, if you look on Intel MPX, this is a similar idea that, again, has been already implemented in some of the newest Intel CPUs. According to what I have read, the implementation is not so great. I mean, the performance benefits compared to software-based bound checking is very minor, and the overhead is of setting up this thing is not good. But yeah, if Intel even does it, so why not try harder? Okay, so to sum up, I really think that we have done, as the microkernel community, a lot of work. First, explaining to people that software dependability or computer system dependability, safety, security, stuff like, you know, things like that are important, and those goals cannot be achieved by using a poor software architecture like a monolithic architecture. I mean, this applies not only to operating systems, this obviously applies everywhere, see microservices. But I mean, we have been always struggling to explain to people that they have to pay some price for these assurances. It's funny that when there are vulnerabilities such as Spectre or Meltdown, suddenly everybody accepts a 5 to 10 to 15% performance slowdown just to get, you know, the assurances we were always thinking we are having. But if we would propose that we can have more assurances, we can have safer, you know, systems, we just have to pay a small price for it. I mean, that we are suddenly being rejected. So let's think out of the box, and let's design our hardware in such a way that nobody could complain anymore. And maybe I also, sorry, I need to mention my colleagues from Huawei who have contributed to the ideas I have presented. But what I wanted to say also, that if you really would like to do something about this practically, I'm opening a new R&D lab in Huawei, which will be located in Dresden. I mean, obviously the location was not chosen randomly. And we would like to have a very balanced mix between basic research, so something like I have presented here, something like 40%, and obviously some practical development. We won't be, you know, making products. We will be an R&D unit still, but we will obviously try to contribute to our product lines, which is also good because we have clear, or we should have clear requirements from our products. And, you know, our company is producing a lot of hardware. And if you would be interested in working on this, please let me know. Please contact me by any means. One side note, we own HiSilicon, which is one of the major one of the major ARM chip producers. So we have the possibility to actually change the hardware. That's it. Thank you. And if there are any questions, yes, please.
Well, maybe
Yeah, just one, please.
Okay.
Okay, maybe a bit of a counterpoint which might support your ideas, nevertheless. So if you look further back in time, there were so many ideas of supporting special features for application runtime systems
Yes.
and whatever, like Lisp machines, Intel's 432, or even the RISC guys from Berkeley who tried object support, and all of them failed. Most of that stuff had been implemented in microcode, so it was horribly slow, but flexible. Now, why did these approaches fail? I think the idea was Moore's law killed them, because regular general purpose processors got fast enough, so it killed them. We're no longer in that situation, so that might be the point in time where it's actually worthwhile to consider your ideas.
Yes.
And we were also thinking in research about some of these ideas, like people have been working on cache-only machines which don't have direct access to main memory and stuff like that. And we're thinking along these lines, and putting this together with microkernels might be really, really interesting, yeah?
Yes, thank you for the comment. Just to quickly summarize for the stream, basically your idea is that we are in the precisely good moment in time to do something like this, because Moore's law is no longer applying and stuff like that. So we need to do something to improve the performance in generally speaking. And I would add to your comment, my comment, that we have RISC-V now, and this is a huge opportunity to actually, create a totally new, open, modular hardware architecture that actually might have some industrial traction. So let's take the opportunity.
I mean, would HiSilicon be interested in building RISC-V systems? Of course, you can't speak for them.
I mean, there wouldn't be in principle against, but on the other hand, we have a full ARM license, so we could even change ARM if we would like. Thank you.